Where is
First grade, I think
No.
it was.
Nope. Hello. Hello. This is the new camera. It is DAC. This same lighting didn't used to look this DAC. This is a fancy Sony thing and I don't know how to configure it for shit. I am done with cameras. So maybe it'll look better soon. I don't know, but it looks wicked DAC for now. I'll see if anyone else shows up in the mail, and then I need to I need to plow through this for myself, finish this, and I'll talk a little bit about the vulnerable protocol when you use a KEM that uses weak binding properties that they specifically cited. Alright. I'm going to go back a little bit. So I left off somewhere in here, I think. Somewhere past here. I think I skimmed through this. And sort of like read through this and was like, yeah, this is boring. Yeah. And this is the like authentication. Fast forward. Yeah. This is sort of like the quote mutually authenticated version. It's not quite. It's just sort of people agree on the same thing. That's mostly controlled by the parameters of the KEM that you use. But I want to go back and basically go over some stuff that I already went over that I didn't care that much about until Cost Kramers read this and sent mail to the PQC forum list, which was managed by NIST and run by NIST, and this is where they had announced the draft of this document, to be like, you've specifically told us about a protocol in a different NIST document, SP, whatever it is, I think it's SP. You referenced 3 of them. One that was based on Diffie-Hellman, one that was based on RSA, and one that was MLChem, I think. MLChem was FIPS 203, it's brand new. The other 2 are not brand new. And NIST basically said, oh, here's figure 4 that I kind of skimmed past. Figure 4 is a protocol you can do, and I think figure 5 is the authenticated protocol. You can use these traditional KEMs based on RSA in here, and that is one example. Yeah, this guy. Yep, they are approved algorithms, all right. And basically, Cost Kramers is basically, if you use this RSA SVE KEM, it's basically a ability to establish a shared secret using RSA encryption, which is like based, like they literally have the functions in the scheme. They just say literally use the keygen function for the KEM equivalent keygen function, use this other function for for encapsulation, and then use this third function. It's called this other thing, but you can use it for decapsulation. And it's like effectively a KEM, and it is a KEM, but I just sneezed off my headphones. It's not a very good KEM, and when you use RSA SVE in figure 4 and I think figure 5, you do not actually come to a shared secret, agree on a shared secret that is bound to the public key, the encapsulation key that you think the person that you are trying to actually encapsulate to, because an adversary can get in the middle, and Eve can basically manipulate the meddler in the middle, or Eve's in the middle can meddle and say, ooh, I'm gonna present a different key and have Alice encrypt to that, encapsulate to that, and I can present something else to Bob, and Bob can encapsulate to that, and they think that they are agreeing on a shared secret between Alice and Bob, but they're not. It's Alice with Eve and Eve with Bob, and they can manipulate it in that way. And this is like a classic error. I'm just gonna pull it up to make sure I'm not misrepresenting the whole attack. It's basically, I think it's an unknown key share attack. Yeah. Yeah, that's me. Why am I not logged out here? Right? No? Hahaha. It's not. Oh, that's a long thread. Okay. That. But first I'm gonna go through the specific algorithm. And TLDR, this is just very unfortunate because the example RSA SV is a official NIST traditional, not post-quantum KEM, and they're specifically citing it as like a traditional KEM and a protocol, a back and forth protocol, how to do a key establishment, both unauthenticated and sort of, checking that, everything is kind of mutually authenticated with over the shared secret. But literally the example, one of the examples they give of using this primitive in that thing is insecure, and it uses and has a vulnerability in it, and it's a pain in the ass. The DHKEM that they also cite, that's in another NIST document, does not have this problem. Yeah, this is why I got through the protocol, but I didn't get to here, which is very funny. So I'll go linearly and like continue to go past the hybrid shit, and then I'll get to that. So the DHKEM that they cite, it's a slightly different variant of like the DHKEM that's specified in HPKE, which is from the IETF, which might be in broader use. They're not exactly non-interoperable, but they're definitely broadly interoperable. Like HPKE DHKEM is quite specified, and the other thing in this NIST document is not as well specified. There's a lot of room to include things or not include things, and that actually changes to like what you agree on and whether the hashing is separated or anything like that. And so it has different binding properties, but it's less a matter of like the binding properties, which are okay because it's Diffie-Hellman. And I think there's been recent analysis to confirm this. I think that's in Klaus Kramer's paper, Keeping Up with the KEMs, like the 7th, 8th, 9th version of it that's on ePrint. But it's mostly a question of interoperability. Anyway, we don't really care about that. We care about the RSA KEM that they cited. So I'm gonna skim. Yeah, this is figure 4. Yeah, this is just literally how to do key establishment using a KEM. in just like a generic protocol. So you decide on which scheme you're using, you decide on the parameters you're using. Alice generates a key pair, spits out the key pair, sends her public encapsulation key to Bob. Bob uses that, encapsulates to Alice's key, and spits out the shared secret and the ciphertext. Sends the ciphertext over to Alice. She decapsulates the ciphertext using her decapsulation key, and also spits out the shared secret. So shared secret, shared secret. If you have followed me at all, you know that binding properties are a thing for KEMs, and I wrote a blog post. It's linked to my blog. It's the only blog post that's on my blog at the moment. I have a couple more drafts in flight, but I'm terrible at writing blog posts. If you see me anywhere else. This protocol is very simple, but the simplicity also means that almost the entirety of this protocol and like what you get, what this shared secret like gives you, is almost entirely dependent on the properties of the scheme, the KEM itself, pi. The binding properties, if it's this thing won't let it be used unless it's in CCA, so there's that. But literally, if this is like classic make-a-lease, there's like I would not recommend to be used in this protocol. Like, we have to do a bunch of more shit, because basically it's spitting out the raw shared secret and not doing anything else with it. So if you were proposing that we use this protocol in production or something like that, even before you get to the binding property shit, you would basically be like, well, don't we want to do session independence, so that we would, meaning if everything, like, we ran it exactly the same, yeah, there's keygen, but there's also a possibility that, like, say you seeded your RNG shittily, so that you spat out the secret key, you source more randomness, and it's all replayed exactly the same. Say you like seeded your keygen, your RNG on your system from like, the start of the epoch or whatever. So you're just literally like, whatever. If you rerun this and you have all the same values, you come out to the same exact. Well, that's actually not a really good example. But anyway, what you would want to do is, when you want to put all your public values into the KDF, the key derivation function, at the end of the handshake of this protocol. So this is, maybe you put your parameters, the start of the thing, into your protocol. That's not a bad idea. And kind of do that in TLS 1.3, for example, because when you're doing the handshake, you're establishing like what elliptic curves you might be using, what extensions you might be using, what signatures you might be using, because you have to offer them, and the other side has to say whether they support them or not, or like start negotiating using them or whatever. So you've got parameters, you've got your encapsulation key. You would stick that into your KDF like as an input to a function. You would concatenate that in, or do it in rounds, the way TLS 1.3 does it. And you would put this ciphertext here, the one that Bob generated. And then you would also concatenate, of course, the shared secret. And then you would probably, like, if you're doing it in rounds, sort of like you do one layer, and you put the output of that into the inputs of the next thing, and you chain and you chain and you chain. This is seen in a bunch of different protocols. And in each layer, you would probably put a label as part of the input of the thing that you're hashing or putting through a KDF function. So like you would put like something into a KDF function, you would be like parameters, concatenate it in like some sort of like ASCII encoded thing. And you put the parameters, or the flag that represents the parameter. And then the next layer would be, encoded label, encapsulation key, and then you have the actual value of the encapsulation key, and you put that input in, and you chain that. And then similar with the ciphertext, and you try to chain that as well with the previous outputs of the previous things. And then finally you have the shared secret key, and then the actual shared secret key value, and then the thing that's you're chaining before. Or you concatenate all these things. I know, Chris. Absolutely. So, the fact that this is like just like raw dogging a protocol, key establishment is just like, if I were reviewing this, I have all these notes. So anyway, before you get to the binding properties of this KEM, that's stuff that you would probably want to do anyway, because it binds to the public values that you are establishing this thing over, so that if someone offers you a different encapsulation key, then you're absolutely coming to agree on a different shared secret for this session. And then if you're using that the final shared secret that comes out of the KDF at the very end, so that if you're doing your, symmetrically encrypted data over this key, it's going to be different than the one offered by, even Alice, who generated an ephemeral key pair in a different session. Because that saves you from negotiating the same exact key that this protocol would have you come out here if, for example, this protocol, this KEM protocol pi, is kind of shit. Some of these KEMs are kind of shit for, reasons, and like they'll spit out the same value. There's some cases with Michelise, but it's mostly about this kind of session independence thing. You want to do this anyway, but this one doesn't. It's just spitting out the raw shared secret. And like MOChem came out of the NIST competition with like this implicit rejection FO transform. So it means that if you didn't come to an agreement, if like the KEM decaps didn't work, you'll come out with a cryptographically long, sufficiently robust, with enough entropy random value. It's not like you're going to spit out 0 or something like that, and everyone ends up agreeing on 0, and it's very breakable. There is that, but it can come out with the same value if you're decapsulating to, with this, I have to go double check. It can fall back, but it's using it raw. It's not binding to the encapsulation key. It's not binding to the ciphertext, and it's not maybe internally. It depends all on the details of the KEM itself, all these details, and that includes the binding. We don't know if the shared secret that's spat out raw and used raw from this key establishment says anything about the encapsulation key that we used to encapsulate to it, or the ciphertext that Bob hands to Alice, or any of that. It's all about the specifics of the KEM here. You can, as a protocol person or a protocol designer or a protocol, doer, can mitigate that by including the, all the public data and the public parameters and all that sort of stuff into your key derivation schedule. You can mitigate a lot of that stuff. It's good protocol practice. It gives you nice protocol security properties to do it anyway. But it's yet another, if you're gonna have different KEMs or you don't understand the properties of the KEMs, it also mitigates the KEMs like being like, whoopsie doodle, like this doesn't actually bind to the like encapsulation key. I think that's the thing with MOChem. If the FO transform fails, come back. No, never mind. There it is. If the decapsulation fails because of the FO transform, it's completely attacker controlled. The value that's spat out is completely attacker controlled, which is a good idea when decapsulation is failing. You don't want to leak anything to the attacker that is like leaking information. So I'm trying to remember. Yeah, so we decrypt, we have message, and then we do another hash function. We put the message we decrypted out and the hash of the encryption key, the decaps key, and then we check that. This is the value we prepare, and then we re-encrypt to see if the value that we get is the same as the value we were passed, and if we don't, we return this other thing. And yeah, it's completely, okay, it's controlled by the ciphertext, which can be high entropy, and the implicit rejection seed or randomness that's encoded in the decapsulation key, and is never used for anything except for this explicit purpose. So it's not entirely attacker controlled. It's controlled by secret data that the key holder only knows and only uses when they're decapsulating, but it's also tightly controlled by the ciphertext. And then if, on the corollary, if everything is working well, the actual key that you use when decapsulation doesn't fail is dependent on the plain text message randomness seed that you encrypted with the public key encryption, and the hash of the encapsulation key, the public key. So what this tells us is MLChem by design tightly binds the public key as long as you have a secure hash function. This is actually encoded into the serialization. It's encoded into the encapsulation key. You can completely rederive all of this from the seed format, so you don't have to hold the hash of the encapsulation key around all the time if you have the seed for the key pair. But this means that if you're using MLChem in that protocol we were just looking at in Figure 4, you can get away, if you only use MLChem in that protocol, you can get away with not including the encapsulation key into your protocol key schedule, because you know that MLChem always binds that in. This is the nice thing you can get, is if you have like a protocol that's like tightly designed around its primitives. But if you don't have a protocol that's tightly designed around its primitives, like kind of your TLS and maybe your SSH and some other stuff, you have to be a little bit more conservative. You don't know if you're going to always be using MLChem. You might be using something like RSA SVE, or I forget, I wrote a whole blog post that includes the classic McLeese and the failure of the binding rules, and I forget exactly which way it fails to bind. I think it's a ciphertext. You can't rely on that. So you have to include the public information, including the encapsulation key, and probably including the ciphertext and anything else you need for the rest of your protocol, which is a little bit more hashing, which may or may not be expensive for you depending on what you're doing with your protocol. But yeah, like this shit matters. Chris says, I feel like TLS and some other protocols expect to get access to the raw secret out of the KEM. Yeah, except TLS does a bunch of other shit with that raw secret. Like it gets shoved into the TLS 1.3 key schedule, the same place that the elliptic curve Diffie-Hellman shared secret would get shoved. And there's a whole bunch of other like key schedules and domain separated and labeled extract and expands with HKDF. It's really, really nice. We were able to get away with the simplest way to do this in TLS 1.3 because the TLS 1.3 key schedule is just really nice, and it just has like a bunch of belt and suspenders that's quite efficient, that saves your ass from weird shit like this. So you could do classic McAleese in TLS 1.3 even though it's kind of huge, and you probably could do RSA SVE in it as well, because of the other stuff that TLS 1.3 is doing for you. So we love TLS 1.3 in this house, don't we, folks? Anyway, I'm gonna go back. Yeah, so that's that figure, and then I'm gonna skip over the static ephemeral because I need to get to the RSA bit. I mean, it's totally doable. It's just actually there's a little bit of debate about, well, HKDF expand is officially a NIST KDM, I think. They have some document somewhere that's like, yes, HKDF expand is like totally checks off some NIST requirement. And then there's like somewhere else where the whole thing, HKDF expand extract, used in a particular setting in a particular way, is also a NIST approved thing. I think Filippo Valsorda wrote a whole post about this stuff because he's been going very deep into getting Go's crypto stuff FIPS certifiable, which is like a whole massive effort. So I think he has the specifics, and I think specifically NIST has NIST labs will validate they'll do their cryptographic module validation, program validation of TLS, and specifically TLS 1.3, and like you can go through the software modules that they have validated, and it includes explicitly like TLS 1.3 like key schedule or key agreement or HKDF or whatever, and it's basically like at least in TLS 1.3 HKDF after you do elliptic curve Diffie-Hellman or you do any kind of key establishment is basically like good, because there's RSA is still supported as like a key agreement thing, I think, somewhere else. TLS 1.3 as at least, and I forget if it's in TLS 1.3. So at least in HKDF, in TLS 1.3 is FIPS approved because they will certify it. All this shit is fucking confusing. A lot of people look at all these pieces and want NIST to just be like, can you please just put out like yet another document that's like, yes, just you can use HKDF full stop with like extract and expand, and just like make it explicitly clear that this is a NIST approved KDF or KDM or, you know, whatever. Yeah, it is fine. It's all about NIST, like, because people spend so much time and effort and money making sure that like whatever thing that they build is theoretically FIPSable, so they can theoretically sell it to the US government or anyone else that depends on FIPS. Because at the very least, if they are one of your customers in theory or in practice, you either have to build two things. You have to build a thing with like a FIPS configuration and a non-FIPS configuration, or you build one thing, and one thing is easier to maintain than one thing with multiple configurations, or two things, or, you know, whatever, or you don't care about FIPS. And so a lot of people try to like really make sure that if they care about this, that they're not going to spend like time and effort and money to get something FIPS validated that can't be FIPS validated, because they might have to go back and rip it all up and do a security analysis and shit like that. And everyone, even NIST, agrees that like HKDF is great and fine. And like I know there's a lot of other people in the U.S. government who like they have a bunch of SHA-2 hardware, and they like HKDF because they can still use SHA-256 hardware without having to do much work. They can just, you know, do it via HKDF and it's fine. Whereas now we have MLChem, and you've got SHA-3, and that's a whole different function, and it's a whole different design, and there's no SHA-2 in there. So like, anyway, it's all just FIPSology and crap. So I'm pretty sure it would be. It's not about security. Everyone agrees that the security is fine. It's about compliance and being validatable as compliant. So, yeah. And another unfortunate, this is the kind of thing I think I talked about on the last part. Shot the reason. Yeah. And for CNSA 2.0, my strong suspicion is that they just have a ton of SHA-2 hardware. So, yeah. And they do not have SHA-3 hardware. It is a big FIPSy mess. It's a kind of a NIST-y mess because, yeah. Yeah, it is. Yeah. Whether the party is gonna encapsulate with EK. Right, static. Okay. Key gens. Okay, sure. Yeah, like this is. I'm pretty sure in the both the hybrid and the MLChem only proposals for TLS 1.3, it's all ephemeral. Then there's like Chem TLS, which is like a different kettle of fish and a big thing, a big different thing, which is kind of like gone in the fridge for now. Authentication, some sort of check is required. Okay. Confirmation derivation. Some applications use shared secret directly, symmetric keys soon. Yeah, and like they designed FIPS 203 MLCAM explicitly to allow this, even though kind of good protocol shit. Friends don't let friends KDF without domain separation. So like even if you that's another thing, especially because there is domain separation within MLCAM between. It uses a different XOF. It uses a different thing to do keygen. It has many different hash functions. They're value secure PRFs in all their different places. But it's hard to domain separate outside of like a whole thing you can control. So like you have SHA-3 in here, and I'm a co-author on X-Wing. X-Wing is a hybrid KEM. We use SHA-3 too. We have a SHA-3 that's the KDF for the hybrid KEM, and then inside MLCAM, which we use as a component, there's more SHA-3 happening. The outside one in X-Wing is domain separated. We have a fun little piece of ASCII art, and the one inside is not. And I know that we can kind of do that because we see more of our larger protocol all the way down to the guts of the component algorithms. And I know it's hard for yes yes, bunch of nerds. What was I going to say? I was already saying something. Yeah, I know that like if you're FIPS, it's really hard for you to like meaningfully domain separate your use of SHA-3 from all the other uses of SHA-3 in the world. But you could do something like kind of good faith, like kind of just like something, just a little something. So if you kind of do it in here, I think it's like, is it G or J? That are actually, yeah, so G is SHA-3, J is shake 256, and H is SHA-3 256. Oh, SHA-3 512. Oh, that's funny. I forgot about that. Huh. So I think it's one of these is, I think J is extracting more from this than the honest one. That's funny. G and J. G. No, okay, never mind. It's the other way around. So, okay. And J is shake? Huh. I'm just realizing that. J is shake, which is like the failure mode of the FO transform of the implicit rejection. And G is the, correct mode. And that's SHA-3 512, and this is shake. That's funny. Anyway, okay. So also, I think this is the only usage of SHA-3 256. You could just domain separate this. You could just have C, your pre-image, and just like concatenate, something here. I don't know, like not X-Wing. MLCAM 512, 768, 1024. Like you could put some stuff in there so that it's not just raw. Like you could do something, but NIST just doesn't seem to like to do stuff like that. And like I bet someone could make a strong argument that that's not super meaningful. Yeah, but there's hashing and pre-hashing, and I do like that they put the OID in. I think that has to do with like the hashing and the pre-hashing and having to identify which one is which. And here it's like there is none. I'm pretty sure they don't even. I think so. One thing that's very clear is that NIST definitely did domain separation by lengths and sizes, which is valid. So like everything in the different parameter sets everything is like differently shaped and differently sized, which is good, and especially within all the functions they use. But yeah, in MLDSA, I think they don't have as much of that, and also they have different hash functions, and they have to identify which one is being used for pre-hashing and hashing and the message and all that sort of stuff. I think that's what that is, but I haven't looked at MLDSA for a minute, at least a couple of weeks. But yeah, if I ran the world and I was dictator, I would just domain separate and just put in the label in all these hash function invocations, no matter what. And then some people might be like, that's extra, you don't need to do that. And I'm like, it fits, especially if it fits in a KEKAC block. I would make sure it fit. It doesn't impact performance. It doesn't impact, overflowing the block and impact hardware performance. And it's just like one little more kind of belt and suspenders sort of thing for protocol analysis and that sort of stuff. But I am not, benevolent dictator of NIST or, Deirdre's private standardization body, nor do I want to at this time. Yeah, okay, confirmation derivation, la la la. I don't love it, but, for bare bones security of the key, all right, that was one of their goals. For other applications, Alice might need to first post-process SSP and KB appropriately and use the results input. Yes. Yeah. Post-processing might include confirmation. Yeah, that's what protocol in Figure 5 is doing to confirm that KA equals KB and reject them otherwise. Sure. Might also. This is basically them doing a MAC with a partial a subset of the shared secret value, and then checking the MAC, and it's like, yeah, sure, all right. That's a way to do it, but you still aren't binding to the public key. They're the encapsulation key. You still have that vulnerability even when you do that, because it's completely determined by the shared secret whether that MAC will pass, and that shared secret is not bound to the encapsulation key for RSA SVE or another weakly binding KEM that does not bind, like whatever, like star bind K PK in the parlance of Kramer's paper. Yeah, it might also include key derivation steps to securely produce multiple symmetric keys from the initial shared secret key, like TLS 1.3. They kind of use it for different pieces. In some cases, key confirmation might also include performing additional computations during the encapsulation stages to reduce the number of communication routes. Interesting. Okay. I think I skimmed this before. Key derivation. Oh yeah. I'm pretty sure this is like this is them like citing reproducing their stuff from SB 800 108 and then maybe 56C, maybe 133, I don't remember, where K concat Z, and then later we're gonna see Z concat like T or whatever, is a sort of like, yeah, you can just like shove a bunch of extra crap in here, and that will, as long as like the actual like key like the K here that you're shoving into the NIST approved KDF is derived from a NIST approved key generating thing like MLChem, or whatever, like something that got spat out of one of the FIPS 202 things. You can basically do whatever you want, and this is basically where the NIST compatible hybrid post-quantum traditional stuff revolves around, because like as long as you put your either MLChem or your P56 secret in this position, you can put whatever you want in the end, and it can be classical, traditional, it can be post-quantum, it can be weird, it can be like putting all your protocol information and all that shit in there, and that theoretically is NIST compatible. There's two ways, two definitions of it, but it's kind of the same. I think this document is the one that says, actually, like, you can put it in wherever position you want, because people were like, dude, I could put my P56 secret in the NIST position now and put like MLChem after, but that is FIPS now. But in like 5 to 10 years, with the timeline saying, oh no, this is going to be deprecated and then disallowed, then it won't be anymore, and that's a pain in the butt. I would love to be able to just like ship that right now, which I can theoretically do, and be like, yay, I am FIPS approved, and I can sell you that product. Putting MLChem first and SecB56 second is like long-lived, but it would take you time to get that construction, that brand new construction, validated by a lab, by a CMVP lab. And there are only so many labs, and they have only so many staff, and there's a line, and there's a waiting list. And if you feel much more confident about your putting P56 first than putting MLChem first, or making that change, like maybe you already have something working like that and it's like an easier change, you would rather not have to do that. I think this document is finally saying in like the next 2 pages, you can put it in any direction, but that's not how it's traditionally been. So there's still going to be like, and this is still a draft, so it may change between, like, there's having a workshop in February or something like that, so it's going to be at least several months until this is final. It's possible that it will change, but yeah. KEMs, on the other hand, by definition, output a key that is ready to use. I would argue that RSA-SVE and other KEMs, they vary, and by ready to use. Key derivation is not required in using KEMs. I feel like that is bad advice. I understand why they are saying that, but I would not agree with that. Some applications using KEMs will require key derivation. Yes. For example, shared secret is expanded to create a collection of keys. Yeah. Specified in SB 800-108, key derivation includes applying a key derivation method to a key derivation key. Method is an algorithm transforming given key derivation key and some other data into keying material, such as a list of keys. Concatenate method is concatenate the key derivation key with option D to Z. Apply a key derivation function KDF. Yep, you just shove that through your KDF and you use the output. In 56C, several key derivation methods are defined for the setting in which the inputs to a key derivation key is a shared secret for one of the key establishment schemes specified in 1 and 2 rather than the caveat. Yeah. This is where we're jumping off. When the key derivation for a chem pi is needed, the shared secret output by pi as in an output of ncaps or decaps may be used as a key derivation key supplied to an approved key derivation method specified in SB 800-108. SB 856E or SB 800 133. In the case where KDM from SB 856 key is used, the shared secret of the KEM is used as an input to the KDM in place of shared secret. Okay, fine. Yep. Section 2, 3. Is that? Nope, we haven't done that yet. All right, key confirmation. That's where you're using the MAC and all that shit. Changing the value can only be calculated correctly with high probability if the key establishment is successful. Yeah. I also think that primary KDF is a mistake. There's too much of a risk before using shared secret in two different ways to screw them up. Yeah. Like, if they updated this to say, if this said you can use MLChem, the shared secret spat out from MLChem, without also putting that shared secret through another KDF, a NIST one or whatever, I would probably feel comfortable with that, because that was designed specifically with that kind of goal in mind, that you could use it, including when the implicit rejection fails, when the decapsulation fails and all that shit. It's not fully domain separated. It's not totally binding to, it's when you use the seed variant for the keys, you're in pretty great shape for the binding properties of MLChem. It's not 100% perfect, but it's pretty great. I would feel comfortable with, I wouldn't be worried. I'm worried about using any generic in CCA chem the way that this language says. I would look at the rest of your protocol and be like, you're doing all this protocol shit, and I think you should probably be using, a specific KDF for that. But them saying, you can use the shared secret spat out of MLChem, a correctly, implemented and not shit MLChem implementation, I would be like, yeah, all right. But any other random thing, like, especially because they found this DH chem and RSASV chem in their other NIST documents, and they're like, oh, look, this is a chem. And it's like, yeah, it is, but it's not. I doubt that it was designed to be used the way that you are recommending it be used here. But I don't know. I'm not. Yeah. I don't like it. I don't love that. This is funny. Key confirmation should be used during chem usage. Definitely won't accidentally chem. Yeah. Enhance the security property of may. Confirming successful establishment of shared secret can also address potential errors. Yeah, I guess. I need to go double check what TLS 1.3 does here. If they're macking the shit out of stuff. I don't know if they are. I don't remember. They mac some things. I forget. There's various ways. Shared secret for authenticated encryption can act as a key confirmation. Yeah, that's true. Then maybe they may. Bleh. I think. What are you allowed to use? You're allowed to use AES GCM, Cha-Cha Polym with 1305. I think you're allowed to use AES counter, HMAC 256, SHA-256 in TLS 1.3. And so if you use your shared secret spat out and you use like part of the key for the authenticated the additional shit, and use the other one for the like actual encryption, if you're able to do your authenticated encryption successfully, then that's doing this key confirmation shit that we will see in figure 5, just kind of implicitly. I prefer that, because you should be using authenticated encryption for your symmetric shit anyway. Maybe for deploying key confirmation, including dedicated key confirmation steps into a key establishment scheme. Method below. Okay, yeah. Sure. Yeah. You just this is constructing your MAC data. Yeah, I think I went over this time. Yeah, you split up your key confirmation key and your data key, and so you wouldn't quite do this. You would do your, you know, AES-GCM style, or you would do your Chachapoly 1305 style, or whatever you're doing. There's probably like a hot and sexy, like context committing authenticated encryption mode that Sanketh knows better than I. That's not coming to me, like OCB or OCB SIV or something like that. That's probably the new hotness. Yeah, and then derivation function not used. The template is yeah, okay. Yeah, AES hot sexy. I don't know how you backronym context committing encryption, but I bet we can figure it out. Okay, and this is similar protocol to Figure 4, except it's doing this key confirmation shit explicitly. So you take your shared secret from encaps, you put it through a KDF, you get your key confirmation bits, your data encryption bits, you do the MAC construction that we saw up here, way up here. And then you MAC over that data with the bits that came out of your shared secret just for that. And then you attach a tag to the message. You include your ciphertext, your tag, the ID that's going into the MAC data, and then this extra B crap that goes into the MAC data. You do your decaps, you get your shit, you reconstruct the MAC data, you verify the MAC tag over the MAC data you constructed with the key material from the beginning of the shared secret, and if it verifies, you continue. Yeah, so if you can probably tell that this still is completely dependent on the properties of the KEM scheme itself, and that if this shared secret does, like, if you look at all the data that goes in, there's a label, there's an identifier that they send you that's public, that's good. There's other identifiers, there's like ephemeral data provided, this is public. Where is it? I'm not even sure. That might be optional. And this extra data that's all public. So that's all public and visible. And any attacker can just copy that. So this is all dependent on whether this actually passes, and it will pass. This is all independent of, well, it depends on the KEM, whether it's independent of the encapsulation key or not. Same as the other one that was not doing key confirmation. I'm gonna skip forward. And now we're gonna get to the hybrid stuff. I think I copied, did a little bit earlier. Hey, X-Wing mentioned, yay, drink. Migration to post-quantum, for example, might initially include multi-algorithm. Yeah, initially, not forever. Include multi-algorithm solutions, combine one new post-quantum algorithm with one tried and trusted but quantum vulnerable or traditional algorithm. X-Wing shot. Yep. Sometimes referred to as a hybrid. Yeah, for example, X-Wing is a hybrid KEM built from two components, MLKEM and X25519. It's also explicitly taking the HBKE DHKEM style and kind of completely inlining it in. So it's not just you're doing an elliptic curve Diffie-Hellman and just like shoving that in there. It's trying to take, you have a long-term public key pair, and then you have an ephemeral key pair, and you do the shared secret, you do the Diffie-Hellman, you have the shared secret, but you're also shoving in the ephemeral public key, the long-term public key, shared secret, and then DHKEM, you have a KDF, and then you use that to actually spit out the KEM shared secret. We're inlining all of that into SHA-3, and then also into SHA-3 goes the MLKEM shared secret, and we prove, my co-authors prove, that when you use MLKEM specifically, the collision resistance of the design is specifically resilient to attacks against quantum computers because of the security of the guts of the thing. And this means that we don't need to include the encapsulation key and the ciphertext for MLChem inside X-Wing. But that's not necessarily true for any other post-quantum chem, even any other lattice-based post-quantum chem. You have to, it's all about the internal guts specific of the component algorithm, about whether you can get away with that or not. And I think we show that if you use the seed form of X-Wing, which is the current version that we specify in our IATF document, you have good binding properties for the hybrid chem. And you go into the guts of the game of how to do that. It's pretty good. I think it's pretty good. I think we have malbind K stuff for part of it, but we need to update that. Yeah, combiner. This is their recommendation for constructing a composite chem. Here we go. Most key establishment schemes of interest can be easily adapted to chems. ECDH chem and RSA chem, which is in the next section. Over the hybrid PQT applications calls for two component schemes, one post-quantum, one traditional. Described below is easily adapted to other cases, such as combining more than two schemes, or combining chems with non-chems. Yeah. And the encapsulation key is just concatenating everything. And then yes, key combine. And what do they define for key combine? For some reason, the focus on combiner really bothers me. The whole thing is the scheme. Okay, this include the shared secrets, the ciphertext, the encapsulation keys, and the parameters. Great. Whatever this is, it's supposed to be a secure PRF, something you would use as a KDF. Maybe P includes a label. Love it. That literally, like, you can practically use it for any, half decent in CCA chem, including the shitty RSA chem, because it doesn't bind, the RSASV chem that they mentioned that we'll get to doesn't bind to its encapsulation key, but your hybrid combiner, your hybrid construction is binding to it anyway. And similar for the ciphertext. So it's pretty good. Feel the need to take a shot every time they still allow what you say. Yeah, they're being explicit that it's going to be deprecated in like 5 years, and then like disallowed in like 10. But in this document, they're like, here's another chem, and like, I don't know. At least making an example of the thing you can use in a hybrid fashion. So like, I'm quite happy with this. I'm happy that they literally were like, wait, and then the question is key combined. So yeah, like, this is actually pretty great. This is, I have a document out there, and I literally called this thing kitchen sink. It's conservative. It's practically bulletproof. It's not the most efficient. But like if you're doing this, like, and you don't know what the necessarily all the components are that are going into it, this will be secure to use no matter what. So yay, good job. And then we look at key combine. Yeah, and since the inputs to key combine include the composite encapsulation keys, the decapsulating party must retain a copy of that key. Yeah, or be able to recreate it from the seed. Yeah. Can be extended. More than 2 components. Yes, you can. And yeah, that may come in handy for multiple post-quantum hybrid things. Okay. In those cases, okay. Still, most multi-algorithm schemes will likely include a step in which a series of shared secrets are combined via the key combiner algorithm form similar to key combine above. In those cases, yeah, okay. Key combiner, some key derivation methods approved in SB 56C. Key combiner approved in 133R2. This is interesting because they still aren't mentioning FIPS 202 and FIPS 203, which is MOChem, uses a KDF from FIPS 202, which is Shake and SHA-3, and like they're still not okay. And minimum key combine accepts 2 shared secret as input. Optionally can accept additional information such as ciphertext, encapsulation keys, parameter sets, or other context-dependent data. Yep. And then it outputs the shared secret key. Let's see. Key derivation methods, key combination methods. Okay, 56C. Collection of improved methods for performing key derivation. 56C key derivation method KEMs applied to a shared secret. Yeah, so this is the thing I mentioned before. Z concat other input, or Z concat T, or whatever. This is where a lot of the hybrid stuff is like really leaned on. Applied to a shared secret Z generated specified in 856A or 856B, along with some additional input. Is this with the like approved RBGs? No, okay, no, it's not. It's the yeah, 56A R3. Ugh. Okay, this is like elliptic curve shit. And and 56B, nope. 133, nope. 856B. What? Oh, RSA. This one's for RSA. Okay. So this is literally the like use elliptic curves and like use the approved thing from those ones with the elliptic curves or RSA. Put your post-quantum shit in here. Twisty maze of specs. Yes. All the FIP shit is a twisty maze of specs. And like to a point IATF is too, but like at least like I don't know, feels a little bit different. I don't know. Can take one of two forms. One-step key derivation could be by applying key derivation function KDF to concatenation, or two-step. Yeah. So this is the extract expand. This is like the HKDF style, and I guess you could make an argument of like absorb and squeeze is similar to. Extract, a randomness extractor followed by expand. So like, if you're familiar with HKDF, like, look, it's HKDF. And then, you know, the extract is putting in the shared secret, assault, and then that is shoved in with other input. And if you want a cool example of this, 3 iMessage. This is exactly what the updated version of iMessage with post-quantum key agreement has. They updated their ratcheting. They updated, and I think they're the first ones I've seen actually deploy the split PRF construction. I think because they were already using HKDF this way, and they were like, "Oh, we can make this work." Let's see. Oh, this is that's the wrong one. Yeah, this one. Here we go. So this is actually deployed in all modern iMessage. Then like all in one is like extract. You shove out the extract and then you pass all that stuff into expand, and then you output two different keys. There's like a ratcheting key and I think like a chaining key. I forget, because they actually introduced ratcheting into iMessage when they made all these updates, which is pretty great. You shove in one of your shared secrets, like say P256-1, as the like keying material, and then you put in like, I think it's your previous root key. Okay, root key, chain key, sort of like the previous state key. Oh, you get this. You shove that. Oh, if you don't have another one, you extract. Rather run expand twice than split the output. You mean down here? No, I think they want. They don't want to split the output. They want the whole thing. I think they want the whole thing. Yeah. They just and they get like 512 out of it. So I think that's fine. So and then like, if you have another shared secret, then you do a different extract with the nuke thing as the keying material there, and then with the shared secret another 2 over as the salt. And this is part of the split PRF like assumption that was shown to be secure, or was proven to exist here for this construction. You can do this here. You can't necessarily do it with all KDFs that look like this. Performance is something they're worried about for iMessage. Yeah, they only yep, exactly. I forget if they ratchet every 50 messages, but they definitely do updated post-quantum share only 50 or so messages, or like 7 days or something like that. Because they establish with MOChem 1024 kind of like the signal style ephemeral pre-keys and shit like that. It's all hybrid, so they have P256 stuff and they have MOChem stuff. And they do that for the session setup. This is like what Signal update is to as well, except I think they're still using X25519 instead of P256. But then the thing that iMessage does on top is that every 50 messages or 7 days, whichever one comes first, they do yet another, I think, MOChem 768, and mix that into the ratcheting keys. as well. So they're updating their post-quantum security every 50 messages or 7 days or something like that, which is pretty cool. I think they're the most post-quantumous, messaging protocol out there at the moment. It's pretty cool. Yeah. These are nice. The one I'm looking at, this is Douglas Stabila. This is his pen and paper, proofs and modeling. And then the other one that I had open first is doing a bunch of proofs in ProVerif. And I forget exactly who worked on those, but there's they definitely hit it from different angles, which is pretty nice. Yeah, and then so we did the other extract, which relies on the split PRF, and then finally we do our expand, where we take the output of that second extract as our key material, and then we have a bunch of labels, and then we get 512 bits out, and then we split that up into a root key and our chaining key. Let's see, no, I'm pretty sure. Yeah, I forget if it's which exact assumptions that. I'm pretty sure it's this split PRF thing, but maybe they just call it something different. Let's hear. But yeah, they are the ones that I'm aware are doing it that way. You can kind of squint at TLS 1.3 and kind of say that it's doing something like that too, and it's been doing it for a while. But it's they do an extract, and then you do expand, and every single one is a labeled okay, this is for this part of the handshake, and they'll have an expanded out that's for the client side originating traffic, and then they'll have a different one for the servers originating traffic of the handshake, and they're splitting it up. And I forget if it's kind of doing something similar to this, which is it's taking keying material from a previous extract and other keying material, and they're putting the other keying material into the salt area or the other input area or whatever. So they're kind of using both of them, but they're slightly different. I don't know if TLS 1.3 is doing that specifically, or if they're just chaining, taking key material from an extract or a previous step and just putting it into the same key material spot, and everything in the additional data or salt or whatever is salt, or literally just label information. Yep, exactly. Expand with different labels or chaining expands. Yep. I think that's the very common usage pattern, and this sort of split PRF assumption of putting secret material in different places, and is that secure? I think that's very recent work in the past 2 years or so. So Apple adopting that for their post-quantum upgrade to iMessage was pretty cool to see. And it's, especially if you're using HKDF already, it's kind of a nice, you can just kind of slot that in there and win-win, as opposed to kind of trying to re-architect. One way you can really do it is just be concatenate your shit and just shove it into that key material place. That would be kind of the first thing I think to myself. But this is cool too. I don't know if other people will be yeah, I'm gonna use this to extract and then expand kind of dealy, but you never know. I think it's pretty cool. Okay, and then yeah, so that's this shit here. My dog. It's required the extraction is applied to the shared secret seed. Yes. Always shove in the KDF. Let you sort it out. I mean, yeah, shove it in the KDF, label it, either concatenate the label or put it in the appropriate place in the KDF, and at the very least, your formal analysis of the thing is not going to find oh, I can take this thing from over here and this other invocation of this oracle and shove it into this other one, and ooh, look at that, I have an attack. You won't have, at least you will not have that. And yeah. Okay. 56C describes the specifically approved choices: KDF, extract, expand, as well as the format and context. Do I have 56C open? Pardon. 56B. 56A. There are too many. There. Yeah, I've opened this before. Yeah. So, yep. 800 108 shall be used to key expansion. Wait. Extraction, then expansion. Okay. Use a Mac, implementation of HMAC, based on approved hash function, which sounds like SHA-256 is. So I think this might say, if you know what you're looking at, that HKDF based on SHA-256 is usable. It's just a matter of like making sure you'll get validated by the lab if you care about that. In either case, or AES-CMAC, yeah. The untruncated output of the MAC algorithm is used as the key iteration key for subsequent expansion. Yes. PRF-based KDF. Okay. Shall be used for key expansion. Prove MAC algorithm as the PRF. Okay. PRF used by the KDF and key expansion is determined. Okay, yeah. Okay. Yeah, this is fucking... Like, if it walks like an HKDF and it quacks like a HKDF, it sounds like you're fucking talking about HKDF. Bunch of other extra shit. Of course, they're not gonna fucking say that. Yeah, SHA-256. Great. Yes. HKDF. So, yes. Yes. Okay, I have to remember this. It sounds like it's literally, like, I don't know why this is controversial then. HMAC-based KDF, we don't like to see HKDF. Yeah, yeah. I mean, they specifically cite it, but like, sure, whatever. That's funny, because now we have to go double check with some people. It's like, how is this not super duper explicitly, transparently clear? Why is this even a question? Okay. This publication approves the application of these KDMs to the shared secrets of the approved KEMs, including the quantity Z. It can be the shared secret of LChem. Yay! Very good, yay! And then this would be your traditional shit, if you want, which I think is the correct way to go. It'll future-proof you even if it's going to take you there. Thank you!
I don't know if she did.
Okay. Yeah. Good jobbies. Okay, and now this is a key combiner, which is different than the other thing, the extract expand thing. One step, two step. 5060 allows the shared secret Z to have the form. Yeah, concat S1, S2. Yeah, that's what we were saying before. Just concatenate the shit out of that stuff and shove it through. She does. She's had a little bit in there, but needs a refresher. So it sounds like at least NIST doesn't like it, doesn't want you to concatenate your shit and then put it through here. They do not want Z to be your concatenated MLChem shared secret and say your, you know, your elliptic curve Diffie-Hellman shared secret. They want they want this to be your MLChem shared secret and your other input to be your Diffie-Hellman shared secret. But for this thing, they do want that to be the one-step thing, which is basically SHA-3 and other stuff. Okay. Okay, sure. Yeah. Yes, you can combine many shared secrets. Okay. This publication approves the use of the key combiner 14 for any T's greater than 1 so long as at least one shared secret is a shared secret generated from the key establishment methods of 56A or 56B or an approved chem. Or an approved chem, okay. Important to note that in the case. So, okay. Okay, I'll get there. Important to note that in the case where the KDM in the combiner 14 is a two-step, extraction is performed with all shared secrets input. What? This is confusing. Let's just be... Okay, as your method, extraction method. So it does let you. Never mind. All right. Fine. Sure. Like, I guess I have to go look at the sort of split PRF analysis to see if there's any, like, meaningful difference between concatenating the shit and just shoving it through, or doing the kind of iMessage style. I have a feeling there isn't a meaningful distinction, but I don't know. Maybe I'll go reread that. 56C allows other input to contain an input that is chosen arbitrarily. Contain the parameters. Okay. Choosing fixed inflow appropriately, we can construct approved key combiners of the form 14. That, in addition to shared secrets, also receive additional inputs like encapsulation, key ciphertext parameters. That's advanced. Yeah. Choose the KDM to be the one-step key derivation method with KDF as hash function H. Sure. Jesus. 56C R2. Do you even mention SHA? I can type. No. 12. Did I mention 12? KMAC? Okay, they do. Alright. Oh, no, they do. Okay. There's too many documents, man. Too many fucking documents. I guess they specify it in FIPS 202 and then they talk about what's approved usage in these other 56 ABC. Alright, so you can use something like SHA-3. Set other input to contain only the concatenation of ciphertext, encapsulation keys, and the parameters that define the key combiner, blah, blah, blah. Okay, then, yep, that's the one we saw before. Can instantiate the composite chem example from 5.5 by using the key combiner. Yep. Composite chem with shared secret whose length is the output of H. I'm worried that the way that this is written, people won't necessarily use this, but they might use this, and this, and this, which is not, well, the way they wrote it, if they're not stupid, if they actually just like connect the dots, if they just replace the other thing with this thing. Okay. Oh gosh, 800, 133. 3 improved methods for combining cryptographic keys generated by approved way. Concatenation, XORing, key extraction, KMAC. Just concatenation, so it's not necessarily better. Yeah, but if you're reading this document and you're like, oh, what are my options for literally dysfunction key combine that was mentioned up here? So far, they've only mentioned one, which is this one. But they mentioned all this other shit that looks similar. That is not a great hybrid chem combiner, in my opinion. So I'm just a little bit worried that people are like, ah, I'll do that, and that will be my key combine. And if you read closely, that's not what it's saying. But I am worried that it's just sort of like, yeah, you might be right. Yeah, and that's aligned with some of the major recommendations from other papers. This is probably citing from or inspired by. Some of these methods can be applied as just a single key. Is it? These methods can be thus used directly as key combiners for constructing multi-element schemes. Yep. Okay. Considerations for composite schemes. Yep. Chosen plain text attack security. Chosen ciphertext attack security. Well-constructed composite chem should preserve the security properties of its component chems. Depends on how the composite chem is constructed, and particularly on the choice of key combiner. Yep. They don't mention binding properties at all. In the case which goal is active CCA security, but only one of the two schemes itself is NCCA. Got around. Yeah, no problem. Thank you. Thanks for joining, chat. Yeah. Yeah, the designer of the composite scheme does not know which one it is. Sure. Well, the whole point is that at least one remains secure. And you want the construction to still retain security when one of them is broken. All but one are broken, such as by a quantum computer. Shown in 25. Just 25. Oh, I don't want to click away. I want to lose my spot. The straightforward key combiner KDF concat the shared secrets that only uses two shared secrets. Does not preserve NCCA security. Thank you. The scheme Pi 2 could be so broken that the combined Pi 1, Pi 2 is not NCCA, even if Pi 1 is NCCA, and regardless of KDF is used. Yes! Very good. Therefore, NIST encourages the use of key combiners that generically preserve NCCA security. Very good. It also preserves other things. Such a key combiner as follows. Let each hash function prove for one step key verification. This is just SHA-3. Key combiner as follows. Gosh, yeah, sure. Yes, the two keys, the two ciphertexts, the two ephemeral encapsulation keys, and the domain separator. Look at that. Yes, uniquely identify the composite scheme. What about the parameters? I don't know. Fuck it. Okay, maybe it includes the parameters. Used to equally e.g. Pi 1, Pi 2 order of composition, the choice of key combiner, and the KDF. Love it. That's it. Oh god, I love that. Security practice. While composite schemes are meant to increase security, necessarily add a layer of additional complexity to the basic chem framework. Additional complexity will be reflected in the implementations and applications to introduce security vulnerabilities. Moreover, adding composite schemes introduces additional choices in protocols, which also introduce vulnerabilities in the form of downgrade attacks. Yes, implementers and users should be aware of the potential challenges in implementing and deploying composite schemes. Oh, sweetie. I'll be right back. Hold on. This fussy girl is my guest. Hey, hey, hey. Don't bite. Don't bite. You're killing me. I'm trying to comfort you, and you're eating everything. Shush. Oh no. Stop. Good girl. Okay. I don't want to touch my camera. Shh. Relax. Relax. Shh. No. Oh, shoot. I went too far. Okay. Nope. Shush. Hey, 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 hey. Crazy. You're crazy. Okay. So far I'm quite happy that the only explicit combiner is the one that's kind of bulletproof. You need to stop. Here. Shh. Shh. Okay. Section 6, examples. No requirements or specific guidance. Aid the reader in understanding some aspects of KEMs are constructed and used in manners consistent with NIST guidance. Examples of KEMs. 3. ECDH KEM, not to be confused with DH-KEM and HPKE, RSA KEM, and ML KEM. While ECDH and RSA features are perhaps not typically described as KEMs. Hi. The goal of these descriptions. Oh, stop. Illustrative only. I still don't love it. Episode 3 already contains a complete description of all KEM. Yeah, okay. KEM from Diffie-Hellman. Yep. Have a long-term key pair to encapsulate. Output is the key derived search material on the subjects. I've read this and I'm pretty sure it's exactly just like you have a long-term key pair, Diffie-Hellman key pair. You create an ephemeral key pair that's kind of like the public key is your ciphertext, and then you do your Diffie-Hellman with the static key pair and the ephemeral key pair, and the shared secret. The ephemeral, your encapsulation key is the static one, and your ciphertext is the ephemeral one. And then the shared secret is the shared secret from Diffie-Hellman. And the way that they define it, they don't have a KDF at the end. They just have the shared secret, which is not the best. But because of the properties of the curve Diffie-Hellman, and the curves, they're not specifying any cofactor curves. They're all prime order NIST curves, and the compression formats and all that sort of stuff. The bindingness of Diffie-Hellman is pretty good in this construction. It's just I really wish they had like an actual KDF on it, like DH-KEM. They don't. They don't explicitly include. They don't explicitly include the the public keys, the ephemeral keys and the public keys, the ciphertext. But they can kind of get away with it, unlike RSA can. Nope. Don't try to leap to your doom. Yeah. RSA, yeah, no, this is your guy. I don't know a ton about the binding properties of RSA schemes, but I'm gonna defer to Plaza's email in a second. So this is referencing SB 856B, and it's, yeah. Crazy. RSA. Crazy. Where is this? Oh, Okay. Oh, section 7.2. Okay. There. This one. Yeah. This is it. Oh, they use generate and recover for encapsulate and decapsulate. So RSA EP or whatever. RSA SVE. Whatever. I've literally not known about it, heard about it. It's probably just another common form of RSA. It was just a name that's a NIST specific name that I'm not familiar with. Yeah, you encapsulate. Output is a secret value. I'm pretty sure. Yeah, and then there's a nonce for key derivation or something like that. Hey, please. Stop. I know. Shh. Hey, please. Yeah. Generate C. Encode it. You literally just encrypt Z, quote, the shared secret. It's just like, it's completely not dependent on the public key. And like the commitment to the ciphertext is like, I'm pretty sure it's completely independent. I mean, if you vary the Z, you may vary the ciphertext, but not deterministically. Like you will not always vary the ciphertext, I think. I'm not 100% sure, but you definitely don't. If the public key changes, it's definitely doesn't have an effect on the shared secret value. So yeah, you can see that it doesn't have any binding to the encapsulation key, the public key. So, and then okay. Oh yes. Do you want to play with the puppy in the mirror? The puppy who is yourself? Is that what's going on? You're so silly. Okay, MLChem. Talked a lot about MLChem before. You can go look at MLChem. Okay. Examples of application of chems. HPKE. Yeah, yes, you can do that. Sending is this just how do you use HPKE? Huh. Keygen. Send the ephemeral key and the parameters. Do endcaps. Hey, no. Don't say HPKE and then just like do a like not great version of it. Sometimes referred to as hybrid PKE. No. Okay, HPKE is the one that's specified in RFC number, not just hybrid public key encryption. Like, oh, come on, don't do that. This, yeah, like, I just get very worried when you're writing down protocols in a document like this, and that people, and they're, like, the authors are intending it to be just sort of like an example, but like, people go look at this like official NIST document and they're like, cool, I will use that, and they will just copy it verbatim, and they don't do the domain separation and labeling and all this other good stuff that we've been talking about, and I'm worried about that. But hello, sharp teeth. News. And I like. You're silly. Okay, static ephemeral key establishment. Yeah. Wait. Okay. I guess unilateral authentication. Okay, is that? That's it. Yay, got mostly done then. Yay. Approved MAC algorithms key confirmation. And generators. Using approved random generator. Yeah. Nonces. They mention nonces occasionally, like for some of the authenticated MAC authenticated stuff. Like whatever. Okay. So I'm just gonna go back to figure 4, for example. Now that we've looked at a specific example of RSA SVE, which does not bind to the public key because of the way that it generates its shared secret, which is just literally a random value and it's spat out, encrypted and decryptedly, completely raw. Shh. You are a silly puppy. I know. 1 second. Where are we? Oh, shh. I know. Here we are. So if we use that RSA SVE, we spit out our shared secret. It's just a random value. It's just a random value sourced from your random number generator. And then you have some ciphertext. And then you decapsulate your ciphertext using the decapsulation key, and you spit out the random value. So if Eve, so this is the attack that Cass describes. And you can, like, I would fix it at the protocol level because I would be conservative about like just shoving a random KEM in there, and you can get other nice protocol benefits out of like including everything in like a key schedule or shoving everything into your KDF, all the public data that goes on the wire. You can get good protocol benefits out of that, whether that's efficient enough for you. Maybe you're hashing in like kilobytes and kilobytes of public data. Like, it's up to you, the designer, to figure out. If you design it very specifically around a specific KEM, you might not even have to worry about this. But if you're allowing more than one, you probably want to be a little bit more conservative. So, option 2 requires strongly binding properties from the KEMs for the example protocol. So, like, I only use MLKEM, or I only use X-Wing, or I only use the key combiner that they mentioned, which is like the kitchen sink. That would be fine. Yeah, that'd be better than what exists. So the attack they described is unintended. What do they describe it as? Yeah, unknown key share attack, because basically you think that Alice thinks that she's coming to agreement. She's establishing a key with Bob, and Bob thinks he's establishing a key with Alice, but they're both mutually coming to agree on different keys with Alice, or at least manipulated and determined by Alice, and it's not actually binding. The key that Alice negotiates is not actually bound to Bob's public key, and vice versa for Bob with Alice when using a KEM like RSA SVE. An example is we assume that these are static KEM keys. Sure, why not? It's just whatever. Eve starts a new session with Bob. Bob uses RSA and caps with an ephemera with Eve's encapsulation key, and obtains a shared secret and a ciphertext. Bob sends his ciphertext to Eve because he's encapsulating to Eve's encapsulation key, even though he thinks it's Eve is, quote, being honest. Eve computes, decapsulates, to obtain the shared secret with Bob, which is Z. Alice then opens a new session with Alice. Eve generates a new key to be, encapsulates to Alice's static encapsulation key. But instead of using the correct random number generator to generate the secret, as specified in RSA, because Alice is a fucking attacker, so she can do whatever the fuck she wants to choose all her values. Like, she doesn't have to conform to some NIST specification. She uses the shared secret established with Bob, so that she generates ciphertext and the same shared secret. She uses the same shared secret on their side, and then the ciphertext, Alice decapsulates the ciphertext, which decapsulates to Z, which is the same shared secret that Eve computed with Bob, or the one that like Bob computed for her. Alice then sends a nonce to the adversary and incorporates it into the final shared secret K. Is this figure 4? Yeah, sure, whatever. To the adversary and incorporates into the final shared. It's just KDFing. It's just adding more material. Yeah. Eve learns the nonce because it's encrypted under the shared secret. Forwards it to Bob, who also incorporates it in their final shared secret key K, where you put Z concatenate with nonce through that KDF we were talking about. Thus, Alice and Bob share a key, but Bob thinks it is shared with Eve. The exact same procedure works for figure 5. The key confirmation step can complete similarly because the attacker knows K and can just confirmation data. You can't do this if with a chem like MLChem, because even if you reseeded the random number generator in MLChem, the shared secret is still bound to the encapsulating key in incaps and decaps. So it would still vary even when Eve is trying to send a manipulated ciphertext to Alice. It's still the same attack could not be used and result in them decapsulating to the same shared secret, with Eve in the middle, or Bob thinking he's talking to Eve and then he's actually like being forwarded Alice, or whatever it is. So that's it. There's some good stuff in here. I hope they change some of the examples. I hope they stop pointing at RSA, SVE. I don't know if they will. There was some chatter about maybe they'll point at some IETF docs instead. Like maybe if they pointed at DHChem in HBKE, it would help avoid confusion and interop confusion. But we'll see. They won't even point at HBKE, even though they're talking about a protocol called HBKE. They do their own thing. But yeah, that's it. I finally got to the end of this. There's some good stuff in here. I'm glad that the only key combiner that they actually specify is like the good safe one and not anything more complicated than that. That's great. That matches something in a different document that I'm writing. Okay, me and this little shark are gonna call it for tonight. Thank you all. Bye.